who wants to start? Well,
So the team is
Who's recording? Can you record?
Yeah.
Oh, okay.
the teammates are Damian Marino, Yannick, Fatima, Eamon, David, and Ricardo Gales. And this is our presentation for this conference.
well, let's talk about each role of the team. We were three people in manufacturing. I was in charge of all the stations of PLC, and assembling it, the sorting system, the conveyor bands, the dispenser ones, and Fatima and Damian will talk about the rest of the part of manufacturing.
It was actually 4 people in the manufacturing team. It was Eamon too. And well, in my case, I developed the station, the whole mechanism and how it was supposed to work. The cup would be entering after the cup was pushed out in the vents, and it will enter here and turn around to the measuring system of the viscometer. Then, if more water needed, it will go here. That is the water ball, and then it will go back and then out. And this thing would help the cup to go out of the station and go to the next vents where it will be selected. And I don't know if you want to talk about it.
Yeah. So for the selection process, I don't know. Let's go back a step to the delivery process. So we had a stack of 3 different kinds of bottles or desired viscosities. So red, blue, and green. Those ones are pushed out by DC motors, and the stack can hold up to 2 cups when the motor is fully retracted. And those 2 cups are detected by proximity sensors. As soon as one of those buttons here is pressed, so if you order red, blue, or green, the desired cup will be pushed out. Then the transportation is all in a separate PLC program. So we have proximity sensors at the beginning and at the end of each band. So that means every time something enters the band will start going until it reaches the end of the band. Then it will enter into the viscosity station.
At the same time that you're explaining, try to perform the demonstration.
Yeah.
Yeah, because
So,
you know it's double time.
yeah. So for performing, right now we didn't have time to hook everything up. We tested everything modular on its own, and now we just started to make all the connections. So I could only show you the actuators, but I can show you a mechanism.
If you want, try to
Show as much as you can.
Yes.
All right. So for the mechanism, I can only do it manually. So we would have, for example, ordered a green cup. That would mean that we can. Oh, wait. So if we order a green cup, we will push out the DC motor. Let's just do it like that. So the cup is pushed onto the band. As soon as it's on the band, the proximity sensor here detects it, and this motor will stop moving forward. Those proximity sensors aren't connected yet. They are part of the how many bottles are in the stack. As soon as this bottle is then pushed out, or one of the bottles will be pushed out. So if there are 2 bottles in the stack, the furthest bottle will reach the band sensor, and that would detect the motor to retract again, like this. As soon as then this proximity sensor detects the detects the bottle, the band will move forward. That I can show right now because we have problems with those DC motors. They have faulty connections. So they will move up until here. There, the next proximity sensor will, when it's connected, detect the entrance into the rotary state. That way, after 200 milliseconds, the band will stop, so it will ensure going into the station. Then the viscosity process starts.
Yes. For the viscosity process, let me just take off the linear actuator. Just wait me a minute, please. In order to show you all the process that we achieved. Let me upload again the routine, and that's all. Well, I could start saying I worked on the design of the PCBs and the microcontrollers part, and especially in this part of the viscosimeter, exactly. And let me show you how it works. For example, it starts here with the time of flight sensor, and then due to the conveyor belt, it detects something here and start moving toward the the color sensor, and then I forgot to move it, but starting is right here, and then after starting 50 seconds, it starts measuring right there. If you want, I could move. I forgot to move the.
Should we redo it? Let's.
Upper one.
Repeat
Yes.
it in another
Yes.
cycle.
Another? Okay.
Lab view using Bluetooth with the ESP32. In this view, we can show you the simulation of what we were going to see if the full integration. This is connected, but I made test, and with a charger in another place in the room, we can have the measurements of what we were asking for. For example, the color tag, the pump, the status, the viscosimeter parts. We were going to have 2 iterations, so that's why we have 2 graphs, the turret base, the stepper motor for the whole system, and the spindle linear motor. So that's basically all the actuators we could have, and also the emergency stop button. And with the implementation of Bluetooth, this was just using the serial Bluetooth class, just adding some prompts for giving us the Bluetooth MAC address, and we can just have the value fixed, and each time I start the program, it's gonna link to the MAC address of the ESP and start reading.
Yeah. Okay. And it's important to mention that all of this work, all actuators and all the things are working within PCBs. There is no protoboard here. And if you want, I can show you while this is working the brake switch. It has an internal one and an external one. But let me upload the code.
And prepare the container to be received by the mechanism.
Yes, so it is ready. It detects and then moves to color detection, that is right there. Detects and goes to the starring. Start going down. Start the starring process.
Why didn't it move a little bit further?
Because it failed the homing.
Okay.
Yes,
Okay.
the homing wasn't that. That was the problem, and there starts measuring. Yes.
And you only tested in a dry run mode, or did you test it using soap?
So. Or what?
Did you make a dry run, or do you have any test using soap?
Oh.
It doesn't retract.
I think because it's stuck.
Yes.
Yeah, but
And-
at this moment you're using a dry run in which you're not using soap or water or any other element. Did you test it with the soap?
Yes. But in Protobort we haven't. Actually, if you can see there is here. This is the master PCB, and this is the slave PCB. All both are connected with the UART communication, and but we missed the part of the resistors for the gains and all that stuff because we left it on the Protobort, and we didn't found like the space for the measuring part right here because changed it a lot. We tried it with another PCB and our gains went like really far from what we had in the Protobort. I don't know why. Maybe, for example, what I assume is the distance, for example, in the shunt, because, for example, there was a lot of copper within the Protobort, and maybe here that we have everything like quite close, changed the gains, but we haven't the chance to prove that. And all actuators work. For example, here is working an actuator, and if you want to pause that working, you just have to, for example, here. Oh, better here. And as you can see, if we activate that switch, it should have worked with the virtual space, but as you can hear, there is a relay, and there is also a relay here that stops all the. See here. Let me remember the pin. In order to achieve that, we take advantage of transistors, and it was the number 2, which is 3.3, and number 2. Oh, well, let me insert it, and the mechanism. Well, the actuators stop working from both. Both are communicated. This slave managed to have all the rest of the actuators that are not these ones, for the measuring ones, and I'm sorry, I removed another one. And as you can see, if we remove the relay, it continue working. It should be within the lab view, but we haven't the time to hit it. And just from that part, I think that was all. And the buzzer. Oh, I forgot.
Yeah.
Yeah, we have songs.
Okay, how many?
3.
Okay.
No, or 2. No. It was one like P just for indicating, and a song. Do you have the?
Why were the songs played right now?
Because I used to have it in the machine state that I had, but I had the problem with that, and I reconfigure everything and prioritize the working. Yes, that was the problem. But we have like the repository and the library literally with the song. And after that, it should have like a move. I didn't achieve to go further, but after our purpose was first measuring, then adjusting, then go measuring, and be sure that we are in in the lecture that the color sensor required, and then go there. If you want, I can show you how it goes off.
Yeah. Yeah, so from that we will receive one message where we didn't find a way to communicate it yet, but we want a message that decides from 1 to 4 if the desired classes 1, 2, 3 are achieved for sorting after, or if it's 4 and the viscosity couldn't be achieved. So that was actually because we did it modular and didn't have the communication between the viscometer and the PLC yet. That was actually managed also by buttons that we said, okay, viscosity 1 achieved, viscosity 2, 3 or 4. So which box is wanted, which sorting box. So
But at this moment, is there anything regarding the PLC working?
no, unfortunately not. Yeah. We could just show you where the sensors are positioned. So the band still is in the same program, so that's actually a separate Arduino with a shield that will detect when this button now, how it's shown right now, when the shield continues, is put out. It will detect here, band will start moving, and prior to getting that message, we receive that integer value 1 to 4. And for that, we have our sorting mechanism that consists of 4 boxes, also with each 2 proximity sensors for the chance to have 2 bottles in each box, and to decide in which box the band should process the bottle, we have a DC motor that runs left to right, and at the back, if you look back here, are metal detection points that will be detected by an inductive sensor.
Okay, a question for those people who haven't done so much during the presentation. So,
Can I finish that process, like how it should
it's
work?
okay. It's okay, Yannick. But the question is, for example, what are the electrical characteristics from the DC motors that you're using, and how do you justify the selection of the components?
Should I start?
The ones who didn't participate. Which are the electrical characteristics from the DC motors, and how those characteristics allow you to choose the components that you're using to drive the motors?
I mean, we chose the motors for
Yeah.
the rolling bands on 2 sides to be like equally.
Have more,
Yeah. And these work quite well. So yeah, we chose them, and they had the right power, the right speed, and everything. Then another motor is at the station. You can see right now. But yeah,
Can you provide any numbers about the electrical characteristics?
no.
Yeah, that's about the voltage, but there's another parameter that is very important for DC motors.
No?
The current.
Yeah.
One of current we use, so we prove it. And with one of
Which is the current, and how do you test it?
with the battery of the military, or maybe we can test it with this one.
Okay, and how do you choose the drivers based on that current?
The what?
How do you choose the drivers for DC motors based on that current? So relate the electrical characteristics from the DC motors to the driver that you choose. Nobody else can answer it?
The driver.
Yannick?
Yeah, so we chose for the 6-volt motors, those are the yellow ones. We chose the basic L293D H bridges because they support up to 12 volts of motor supply voltage, and they are able to supply enough current to work on one H bridge, work 4 of those motors. So we connected to one of those H bridge channels 2 of the motors parallel, and that is what was our what we wanted to achieve, to have as low of H bridge connection as possible. And for those ones, I can say that we chose also the same L293D H bridges because those are also 6 volts, 130 RPM motors. And we didn't supply them by one channel. We did supply them each by one channel and 2 motors and 1 H bridge that will ensure that we have enough current flowing. And I can show it right now, but it worked really well. We didn't use a PCB for the PLC part. We used on the market there are those Arduino shields that consist 2 L293D H bridges where we can directly connect those motors and work with that directly, because for us the only stuff we needed on the PLC was motor control and signal processing of the sensors, of the proximity sensors or the buttons. So from that part,
You want to complement?
Yes.
Yes.
For example, besides the motors from the PLC part, we have also both these DC motors, and these ones we managed to control it as DC motors. And for example, for these, we used also the LMD23D, but in SMD package, because the SMD package had like more pins from ground and more capabilities for source for heat consumption. It like enhances that consumption, and also because we saw that these ones in order to have like the best charge possible, because we made like proofs like firing it, the LMD23D haven't had like the performance that we expected, and we actually burnt one of those, making the efforts against the linear motor, and that's why we chose the SMD part. And for the measuring part, we choose the TB1266 due to because the LMD23D haven't had like the starting point, the starting voltage ranged from 3 volts to 5 volts. And if we needed, for example, to spin that spindle at 30 RPMs, we needed like a duty less than 3 volts, and it won't work with the LMD3D. So we choose the TB6, the TB modules, these ones here, due to the capability to be activated with 3.3 volts or less. And that's why we choose those H bridges for the DC motors in the microcontrollers part.
Can you explain a little bit more about how can you control a stepper motor?
Yes, stepper motor could be controlled.
Someone else, because you have already answered.
I mean, a stepper motor, I think we first had the problem that our battery was too weak, but I can't remember, right? It was a couple of days ago. Yeah, I would say you have to choose the right battery.
Well, that's a question more for industrial automation. So
Don't worry about
don't
it.
worry about
Okay.
it, yeah.
In your case, don't worry about it.
Okay.
yeah, I could say it, but
Yeah, you have already answered.
So in the case of, for example, the section of the viscosimeter, we just like needed to implement the
classes previously that we used to work with PWM, encoders. We were like,
The stepper motor, how does it work? The driver you're using?
the driver,
Yeah.
just the motor or with the driver?
With the driver and motor. Driver and motor, how do they
Let's
Yes.
say, how do you control
Yes.
the stepper motor using your driver?
Yeah.
That's the question.
Yeah. Okay. Well, we need to first connect and manage to put in the ESP with the drivers the directions and the enables that are gonna work with the stepper motor. This because it's gonna give us the possibility of providing it the direction that we want to use it, like counterclockwise or clockwise in this case of the stepper motor, and also the how to say the resolution, I would say, or like the degrees we want to work out. This is with the also with the enables, I think, and just like having a how can I explain it? Like when it's gonna go clockwise, like I have the the degrees of the steps it's gonna have, but also like managing, like for example in our case, it goes like an offset of the motor, so we need to implement like a kind of reduces or like manage the error it's having, and this is with also with the driver.
I still haven't heard how actually the driver works. Do you have already answered?
Yeah,
So you
could I
don't-
compliment?
No, someone else. So there's still two of you who still haven't answered something.
I was thinking the same of like, for example, in the station, like what you need to do is the range of 90 going
Yeah,
to
but
the.
how do you apart taking the driver and the motor apart from the station? How does it work?
How does it work?
The driver and the motor.
At least explain how you can manage to control the stepper motor.
Like with the communication in both of them, or
No, just the driver and the motor. What does the microcontroller send to the driver so that the motor moves?
And how are the signals that the driver sends to the stepper motor so it can start moving?
What?
wasn't it
With the
when we were
sensors.
talking about of the
No communication. It's just the driver and the motor.
Let's say that you're starting to develop the first practice driving the stepper motor. You only have the driver
Isn't it
and
with
the
the
stepper motor.
frequency that we were talking about like
And the
earlier and the
PWM.
Yeah.
Okay, so
Yes.
explain because you're taking a lot of time.
Not just, well, it just works like we have the two pins enable and this one. Two enables, the ESP is gonna send a binary code. Is gonna let the driver know which direction, and only we need to implement the full PWM like value is gonna have like we can set the value by ourselves depending on how many turns or how many we want to like
It's
advance.
not the PWM value. What is it?
So the frequency, the maximum frequency and the minimum
Okay,
frequency.
how do we handle the frequency so that we can drive a stepper
It's
motor?
in a, I think it's in a range of 30 and 40. The frequency, like you have to, the frequency that has to be sent.
Okay, well,
Could I compliment something? Yeah. We made like in order to know the best microstep and what convened us the most, we made like an analysis. We calculated the maximum velocity and the minimum velocity and the torque that it required depending on the microstep and the frequency that we applied, changing it by the PWM library, you know. And having this, we made conclusions. For example, with this frequency, it worked, but it was like too high speed, for example. And with this one, we chose, for example, what you saw there was with a microstep of 4 and with a frequency of 300 hertz due to the amperes that it allowed to work like two actuators together and the limitations that we found. and it works actually activating. Obviously, you need a duty. The duty doesn't matter a lot. It is just to activate the voltage throughout the stepper motor, and what changes the velocity, what matters is actually the frequency. And if you increase the micro step, you reduce the torque. So it depends. For example, here we charged it a lot and made an analysis depending on how many are we gonna like charge, and the velocity that we needed for the homing routine and for removing the things. Depending, for example, we made in the last routine we considered how full the cup it would be, and depending on that, we changed the velocity depending on the frequency.
Okay.
But we could not like show you that.
Okay.
Okay.
I think that's it.
Yeah, that's enough for me.
All right.
Okay.